Patil from Indian Institute of Science, Bangalore. He's part of the solid state chemistry unit there. He did his PhD from BAM University in Aurangabad. His bachelor's degree, and then he went on to do his PhD from Germany, working in the area of polymer chemistry. He has been at IISc since 2006 and focusing on a whole range of projects, including molecular electronics, and has won several awards, including the Swami Fellowship and the INSA Young Scientist Award. And today he's going to tell us about some recent work they have been doing. So let's welcome Professor Satish.
Thank you. Thank you. Yeah, I'm audible in the back. That's fine. Yeah. So very good afternoon. Thanks for coming for this talk. Indeed, it's a great honor. So let me just thank Professor Gopal, Pratap, and all the faculty members in Condensed Matter Physics Department for inviting me here. So having said that, I'm also equally nervous because by training I'm an organic chemist. So I'm going to talk mainly the physics aspect of semiconducting polymers in this audience today. So the title is mainly the rational design of semiconducting polymers for electron transport. So this is, I will describe our journey from last 10 years. We are trying to design the polymers essentially for electron transport. You see the semiconducting polymers have a dominant p-type character. They are very good hole carriers. So there are very few by design you have to achieve to get something achieve as electron transport. So our research is all about that, how to design a conjugated polymer for the electron transport. So electron transport is absolutely necessary for several optoelectronic applications, but since the discovery of the pi conjugated system, there are excellent hole carriers and very few are electron transport materials. Before I go to today's topic of discussion, I will deviate a little bit and show you some of the few projects which are going in the lab, our group. So this is all the physics we do in collaborations. So we are a bunch of chemists in our group, we synthesize the materials. So it's a completely wet chemistry laboratory, and everything is, all the device data what I am going to show is nothing is done in my lab. So it is, everything is done in collaborations with a large number of people here. Is my very close friend of mine in Imperial College London, Thomas Anthophilus, he does transistors for us. Richard mainly does transient spectroscopy. Now recently we have active collaborations with Jyotisman Dasgupta here in TIFR for transient spectroscopy, and Professor K.S. Narayan is a neighboring institute in Jawaharlal Nehru Center here. We do also a lot of physics, we try to understand the physics aspect of. So these are the wonderful two grad students, actually they really put us at a global map rather. Catherine Kanimojis, she was the one who made the excellent N-type conjugated polymer, and still we are trying to understand what she made in the laboratory from last 4-5 years. So this is the polymer she developed during her thesis, and Tushita just took over from Catherine, just try to understand by developing model compounds. And there is a postdoc from Puttraju, and then the bill comes from all these folks. So this is the current research interest. Currently we are always in hunt of organic solars is all about number business. So we are looking at one of the best molecule where we can make it for organic solars. Some of the new methodology, some emerging new methods we are developing how to get the best solar cell efficiency for organic solar cells. And there is singlet fission organic semiconductor. Palash was just talking in the next room here. So singlet fission is an exciting area of research where we develop materials, and TIFR we do a lot of transient spectroscopy. And this is N channel because I am going to only focus today on this part of the theme. But there are, these are a bunch of themes. We also look at the in a OLED area, thermally activated delayed fluorescence, and collaborations with little bit electrochemical energy storage devices. So this is one of the major grand challenge in the solar cells. So let's start with the one project what we are interested in the solar cells. So soon after shining a light, let's take a conventional p-n junction silicon solar cells. Soon after the shining a light, you generate these Mott Wainier excitons. So you have free hole carriers, electron and hole carriers. One of the major loss where people are trying to figure it out is these hot carriers. So one of the major loss is this thermal loss in an excited state, and that essentially called as excess energy above Eg is a loss in the form of heat. And this is a beautiful paper, Shockley-Quaisers is a theoretical paper which was published in 1961. You see they have in their calculation they took into account this is a major loss, and since then people are trying to figure it out how to collect these hot charge carriers. So this is a major problem in the field of solar cells, any solar cells, whether it's a silicon or it's organic or quantum dot based solar cells.
You want to take that energy away so that it doesn't dissipate as
That's right. That's the idea
so
basically.
some other mechanism.
Yes. How do you collect that one? So no matter what you do is the maximum of a circuit which we get it from Fermi levels. So that's a maximum you can extract as a work out of the solar cells. So this is the solar emission spectrum. You can here clearly see that the distribution. So this is the gray area here typically where silicon absorbs up to 1.1 micrometer. The high energy photon we lost is due to heat. So there is no way you can collect these high energy photons, and there are losses which occur here at even near IR also. So the available energy which based on Shockley Quasar calculation is close to 33%. So they calculated for 1.46 as a band gap. So this is not essentially valid for silicon. Silicon it comes to around 29%. So major you can extract from is silicon solar cells is 33%, and experimentally people are trying to hit those numbers, basically how to encounter these losses. So what this is our design, this is our proposal for singlet fission. If you use singlet fission, let's take again a conventional silicon solar cells. So we want to have this low energy photons, silicon absorbs here again, okay, and we want to coat it with organic semiconductor on top of that. Once we coat it here, we want to just capture these high energy photons. So because these are the high energy photons you are losing in the form of heat, this is the thermalization loss. These two photons, if they convert into 2 excitons, means we can boost by using a fission mechanism, then essentially this is again a calculations which comes from a theory group. Single junction solar cells is a function of band gap. You see the maximum efficiency here. If you use this technique with the singlet fission, you can boost the efficiency up to 40%. And silicon efficiency is currently stagnant. Any appreciable enhancement in the efficiencies, community is going to appreciate that. So currently efficiencies are up to 25%, let's say, for a lab made cell, but if you use this concept, can you boost the efficiency? So with these questions we started working on currently on how to design the material which can show a singlet fission mechanism. So this is the one project. So yeah.
So you are talking about taking a high energy photon and splitting it into
multiple
so
they can be collected at the silicon.
Silicon.
Okay, so that way we can boost the
frequency conversion.
Yes, sort of. Yeah. Okay. So this is the work which comes from here again in collaborations with TIFR. Our group is specialized in making this pi conjugated polymer. So it's a diverse audience here. I will describe you why we make this polymer first of all. What is our interest? We are not interested in generating a large number of library of material. This polymer has a very specific structure. If you look at here, this is the acceptor, means it has a very high electron affinity, and we have a donor which is a pi bridge here, and we separate it out. So this is a donor acceptor and we separate. So we do have a donor acceptor separation. So here we can have a donor, and this is the pi spacer and acceptor. So this bridge which connects to donor and acceptor has an inherent torsional disorder. So this single bond can rotate. So essentially this can lead to again loss in an excited state, typically in organic solar cells. So this is I am talking in the context of organic solar cells, not in the silicon solar cells. So Jyotisman used femtosecond Raman spectroscopy to understand that. So this his thesis is all about what are these losses? Can you really freeze this bridge? Can you really make a semiconducting polymer where you can really freeze this rotation of this bound between the donor and acceptor? So we are interested in making a semiconducting polymer where we can freeze and really somehow encounter the losses in the excited state. So this is another project which is going on. In LED, you can see typically you have a 2 spin half particle, you inject it, you generate essentially by the orientation of a spin, you generate 25% singlet and 75% triplets, and these triplets are completely, we don't collect it. The emission whatever comes in LEDs purely comes from the singlet state, not from the triplet state. So our idea is how to collect these triplets. So I will show you that this is a very challenging molecular engineering. So with this problems in hand, we can set up now a goal. How are you going to do a molecular engineering to address these problems currently in optoelectronic devices? So what we try to do is a typical Jablonski diagram here. So if this exchange energy determines the gap between singlet and triplet, okay, for a molecular semiconductors. So if you push this up, okay, by some way means, I will show you how we do that. We can collect it back at room temperature. Means we are harvesting these triplets. In LED we generate 75% triplet, and these are completely lost. So you can collect those, and if I push it down further and make half of this energy, then I can get a singlet fission. So, this is very, very challenging for a chemist to design the material and to collect the triplet at room temperature, which are very useful for LED applications. And if you make it half, then you can typically see a singlet fission in those materials. So, with this exchange energy becomes a sort of figure of merit for us, and how you are going to collect this one. So, this is the major ongoing activities. Now, coming back to today's theme, so I've deviated a little bit to just show you a couple of projects which are going on. So, let's ask this question: what limits the mobility in conjugated polymer? So, conjugated polymers are beautiful, colorful material for chemists. They are very excited about it. You can tune the color, you can change the backbone, you can tune the band gap, you can do a bunch of things with the pi conjugated system. But for the physicist, they look with horror if the materials are full of disorder. So, okay. So, the disorder, the origin of disorder can be multifold. Okay. So, this is a single chain of a polymer I have shown here called MEHPPV. This material is very well studied in the literature. So, if you look at here, so typically you have this overlap of pi orbital here. So, the delocalization is throughout this conjugated backbone. But during the synthesis, one of the disorder can be a break in conjugations. Okay. So, while chemists make in the lab, you can have a tetrahedral carbon within the backbone. So, that really completely localizes the charge. You can have several conformations for the polymer. The literature is very rich in terms of protein folding. If a protein is considered as a polymer, depends upon what environment you provide, the polymer can have multiple conformations. For example, look at this one here. So, this is the paper which is Paul and my colleague Bachi wrote around 2000. They try to study the possible conformation of the polymer. That depends upon the stiffness of the chain, how rigid your backbone, they can adopt a multifold conformation. Stiffness is one criteria, but if I start processing the different solvents, they can really form a different types of toroids. You can have a bunch of fibers coming together. So, it's a whole range of conformation, and there is no currently experimental tool available what conformation polymer adopts. Okay, how are you going to see that one? And how are you going to repair the defects in the conjugated polymer? If you want to have a bunch of fiber like this, ideally suited for a device then how are you going to, can you really reproduce those things? So, it's a very, very sensitive this structure, because if you change little bit any conformation, if you have a longer alkyl chain for the solubility, or if you change the backbone, make it very stiff, you can have a different structures altogether. So, there is no way we can control, because in the sample, so heterogeneity is very wide here. So, how are you going to control? This is the defects in a pi conjugated system. So, this is still an open question in the community. How are you going to study that? The other problem is spin casting. You take this solution. So, one of the major advantage semiconducting polymer community says is everything is solution process, nothing has to be done in a high temperature. When you cast a film, how this pi conjugated system is going to aggregate on the surface? It typically depends upon the substrate energy, but ideally speaking, you have to have two different possible packing. You can study by X-ray, we will show a lot of X-ray data. Here, the alkyl chain can pack this fashion as this fashion. So, we called it as face on, edge on. Face on is like pi stacking, edge on like a book, like a packing. So, ideally speaking, if you have a semiconducting polymer packed in this fashion, you can expect a higher mobility, depends upon what devices you are making. And if a material packed like this, you have inherent defects within the pi conjugated polymer. So, this is again we cannot study, because typically you make making a field effect transistor, OLED or SOLAS cells, you make a film of 100 nanometer. So, how the polymer packed on the surface, it depends upon several parameters. So, this is again an open-end question, how are you going to really pack a particular way polymer on a substrate. So,
why should the out of plane propagation be?
So, it is a bit basically if you make a FET here, you can expect a transport through pi stacking as well as through a spacing, because your alkyl chains are interdigited like this. So, you have a very close overlap between the side neighboring chain. So, they can hop from one side to the. So, the hopping sites will be, so you need minimum activation energy in that case. So, this is what I am talking about, because your density states are Gaussian distributed now. So, you have localized states essentially. So, you have a large number of localized states due to these defects in a pi conjugated polymer, and these defects can be from anywhere. So, there is no way we can understand from where these defects are coming from. So, this question, so we have what governs the mobility in a pi conjugated polymer are electronic properties. The conventional wisdom is basically soon after discovery of the conductivity in a semiconducting polymer, you see that this is the delocalization pathways for the charge carriers. Okay, so it's a pi conjugated backbone, but can you really stack structure in this fashion? So what governs the mobility? Electronic properties and microstructures. Soon after you say microstructures, there is no way you have any thumb rule here saying that I will get typical this microstructures. Okay, so this is what happens eventually. So this is not actual real mobility, but I try to compare it basically. You see that you can make a statement. You don't find band like transport mechanism in a semiconducting polymer because there are no bands there essentially. Okay, so you have localized states because of these defects. Low charge carriers mobility inherently the property of the material. Okay, so you can see that because they get localized due to all these defects. If I compare with crystalline silicon, organic crystal, disorganic solids, mobilities are in the range of 10 to the power of -5. Okay, typical FET mobility if you consider. So then this mobility really limits the application. Currently people are trying to make, for example, we have some like you want to make an RFID tag, right? So like Walmart makes millions of like goods, and then if you have an organic printed RFID tag, which is you can print it for 1 cent, it is a fantastic application. But currently the applications are only here because the charge carrier mobility for these materials are extremely low. So if you want to make, you can of course make a good OPV out of it. Photovoltaics, we do not necessarily have to very high mobility, but eventually you want to get these applications for like for a conventional semiconductor, these are very well known applications.